Thank you. So this is really good. Thanks everyone for coming. This is brilliant. We kind of had an idea to sort of try and get some people together. I think after the Web Audio Conference in Paris, there was quite a lot of people said, I'm in London, we should get together. So we thought we'd try and put a meetup together. And lots of people wanted to come, and lots of you are here. If this is the kind of thing that you'd like to do, and you want us to do it again, then let us know, and we'll try and work out a way of doing that. A huge thank you to Sole and Mozilla for hosting tonight. That's a perfect place to kind of have something. I think it's nice and quiet and comfortable, and everyone fits in here, and it was low stress. So that's great. Thank you to BBC R&D for the pizzas. That's very kind. They're always hiring. The BBC are always hiring. BBC.co.uk careers. I don't work there anymore, but I used to. In Paris in January, there was the first international web audio conference, which was run by IRCAM, who are kind of a music computing research institute that existed in Paris for a long time, since the late 60s. And so they hosted a first conference, got a lot of people together to talk about web audio, and they asked me to give a talk, which I did, and I'm going to do that talk again basically tonight. So if you were there, you've seen this, but hopefully it's interesting for those that weren't. Yes, sometimes I give different talks, but not today. So I'm going to talk about the origins of computer music. So we're going to go back to the first people to write programs to make computers play music. IRCAM, where I gave this talk in January, they were very influential in those early days, and they kind of had a big influence on what happened. So some references that I'll make were to them. So IRCAM was a music research institute founded in 1970. President Pompidou asked Pierre Boulez, who's a kind of contemporary composer, French composer, to found a centre for research in electronic music. I think he actually asked him to run the orchestra for the country, direct the national orchestra, conduct the national orchestra. And he said, no, I don't want to do that. I kind of want a lab where I can do what I want. And so they gave him that instead. But a lot of the people that he invited to kind of get involved in those early days had kind of already been working in computer music research. So computer music research had gone back pretty much until when people first started using and programming computers. And that's kind of what I wanted to talk about. Can you see these slides? Yes, good. Okay, so to tell the story of kind of the early days of computer music, we need to go back to Bell Labs. Bell Labs was a research department. It was kind of formally founded in 1925, and they were interested in kind of bringing to market and developing kind of Alexander Graham Bell's telephone. So they were a kind of technology laboratory that were aiming to find a way of bringing the telephone system to the mass market. And as time went on, the kind of business grew around telephones, and people realised that they'd validated that idea. People wanted to be able to use telephones to do things. And so the engineers and researchers that they kind of gathered together at Bell Labs to do research into this technology were tasked more generally with exploring kind of the fundamentals of the science around kind of communication. So and what became digital communication. But Bell Labs was responsible for the development of a lot of technologies that you're familiar with. So the originators of the transistor, the laser, and they did a lot of work in kind of software and information theory. 8 Nobel Prizes that were awarded to people who completed their work at Bell Labs. So they were a kind of very influential sort of scientific research institution. And one of the areas of research that they were particularly interested in was compression. So that's how do I send the most information over a wire using the least amount of bandwidth, effectively. And you can kind of see how that would have a lot of applications in communication. And so one of the areas that they started to work on was how could we synthesize speech using digital computers. So there's a couple of researchers there, Carol Lochbaum and John Kelly. They've been working on an early computer program to synthesize speech. And it was one of the very first examples of what we'd call today, if you're familiar with kind of different methods of synthesis, we call that physical modelling synthesis. So they modelled the vocal tract in a person as like a series of tubes with like air flowing between it. And then they worked out like what are the parameters of that physical model, and they kind of worked out those parameters of that physical model by taking X-rays of people. So like how big are the tubes and like how fast can the air flow, and then you build a computer program that will like reproduce speech using that. And so the point of that is that if instead of taking speech, passing it through an analog to digital converter, so converting like what we call sampling now, kind of converting that analog signal that you record into digital and then transmitting it over the wire, that needs a lot of bandwidth, because at the other end you take all that digital data and you kind of turn it back into analog and you can play it out of a system. But if you've got a physical model that you can use, then instead of doing that, what you can do is take the speech, work out what parameters of the speech synthesizer you need, and then just transmit those speech, like those parameters over the wire. So you kind of save bandwidth. So that's why they were interested in it. Into that environment, this was about 1954, there was a researcher who joined them called Max Matthews, and he was an electrical engineer. He'd done his education at Caltech and his PhD at MIT, and he joined the audio research department at Bell Labs, who were working on kind of new and better ways to compress and encode speech. And his boss was a guy called John Pierce, and he was very supportive of giving the engineers at Bell Labs the freedom to work on kind of whatever they wanted alongside their kind of research. It's quite a free environment. And Pierce was a big fan of like contemporary music. And he was attending a concert one day with Matthews, and he said, well, you're working with computers and speech synthesis, like could you get them to synthesize music instead? Like would you use computers to make new music? And so Matthew started working on a program that he called Music, like capital Music. And this was a computer program which could kind of synthesize arbitrary sounds. And so he was developing this program, and he was working in this environment, and he was talking to Lochbaum and Kelly, and they decided to put together a demo that would demonstrate like the capabilities of like speech synthesis and music synthesis. And we're going to listen now to like the composition that they did as that demo. I can't hear it.
I don't know. You could use the microphone.
Yeah, just unplug it
Yeah,
and see if I can.
I've done that.
It's not high quality.
Yeah, that could be the best option.
Let's try this.
It's cheaper.
Yeah.
Yeah, just.
Yep. Let's go. Hear that? So some of you might recognise that song because it was used in Arthur C. Clarke's film, Kubrick's film that was based on Arthur C. Clarke's novel 2001: A Space Odyssey. And so Arthur C. Clarke was visiting Bell Labs and he heard that kind of demo, and they say that's what inspired him to use that song in the film. They say that when Kubrick heard it, he didn't feel like the speech kind of, the way that the singing was happening kind of conveyed the right tone for it, so he ended up using kind of an actor to do that. But it was this idea of a computer singing that kind of inspired him. Let's have a quick listen to the beginning again, hang on. So that musical accompaniment to the speech synthesis was arranged by Matthews using an early version of this music software that he developed. And you can hear that the computer is synthesizing a sort of piano or organ-like sound. Remember, this was like 1959, 1960, that kind of time. Matthews, who was a violin player as well, he kind of a trained musician, he took to calling the computers that he was working with a universal instrument. And so what he meant by that was this. If you have a waveform, which is a kind of variation of sound pressure as a function of time, we can show that if you represent this waveform as a series of like equally spaced values, so at every point of time you have a value, and each value represents the level of the waveform at that particular time, then this string of numbers that you can represent the waveform as is sufficient information to perfectly reconstruct the sound from that list of numbers, assuming that the frequency of the sound does not exceed a certain upper limit. And we call that, at least in the West, we call that the Shannon-Nyquist theorem. It's named after two predecessors of Matthews at Bell Labs, Harry Nyquist and Claude Shannon. So if you take this list of numbers and you generate from it a series of impulses of the correct amplitudes, and pass the sequence of pulses that you created through a low-pass filter, then you perfectly reconstruct the original sound. And the only question you really have to answer is what sampling frequency, so like how often do I need to record one of these numbers? And that depends on the information that you want to transmit. With musical information, when we talk about music, then kind of our own biology works in our favour. So a young person with very good hearing is sensitive to frequencies up to about 20,000 hertz. That means that in order to generate any possible musical sound that any of us can perceive, we only need to sample at twice that frequency, which is around 40 kilohertz. So as long as we have a single number, 40,000 times a second, then we can kind of create any sound that we can call music. And that's what Matthews meant when he said that the computer was a universal instrument. But you wouldn't want to write a piece of music by having to specify what the amplitude of the waveform was, like 40,000 times a second. So what Matthews needed and what he developed was a higher level language that you could give to the computer to generate those numbers for you. And he realised that musicians already have kind of a compact, high-level description of the sound that they want to make. And we call that a score. And so he used the score as a starting point. So on the screen is a description of a kind of simple monophonic melody. There's a single instrument playing a sequence of notes at particular times and pitches. And the amplitude of each of the notes is kind of open to the performer's interpretation, but there's guidance under the score in terms of like the dynamics markings. So that's kind of a fairly compact representation of like a piece of music. And here's the same piece of music as we just saw in the score, written using Matthews' music language. So this particular code is written in Music 5, which is like the last variation of the language that he specified. So I thought I'd go through it a little bit and show you how it kind of works. So these lines that start with not, they describe notes that are going to be played on the piece of music. So each line starts with the instruction, play a note, and it has a time that it must be played. So let's play it 1 second into the piece. And you say, which instrument do I want to play that note on? So there's only one instrument in this piece of music, so we say play it on instrument number 1. The note has a duration, and here it's like half a second. And then the rest of the line is like some parameters that you might give to the instrument to play the note at that time. So in this case, it's the amplitude of the note and the frequency. At the top of the score, we define an instrument called instrument 1. It also takes a time parameter, so we can say like this instrument has this definition at this point in time, and we can change the definitions of the instrument as we go along. And then inside the instrument definition, we kind of have the guts of what this instrument is. So we define, in music, we define the instrument in terms of unit generators that are connected together. Music was the first language to use this paradigm of like we've got kind of building blocks within our instruments that we want to connect together into some kind of graph. So here the instrument is an oscillator which is connected to the output, so it's really simple. And the oscillator generates a kind of repeating waveform, like a sine wave, and we give it some parameters, parameter 5 and 6 here, which give it the kind of frequency and amplitude. The only thing left is just to say what waveform are we going to have in our oscillator. So we might have a sine wave, but you can also generate a function that you can use and pass to the oscillator. So this line says generate a function at time 0 and store it away so we can use it. And the rest of the line defines this kind of waveform. So you define it in terms of like the points in time. And so it's somewhere between a kind of square wave and a sine wave, this waveform. We have a sample at point 0 is 0, and then the next sample, we define a point at sample 50, and we say it has an amplitude 1, and so on. We just give it a kind of a series of pairs, like time and amplitude pairs. So when I was working on this talk and kind of researching the sort of this early language, I saw that piece of code that I've just shown you in a book, which is called The Technology of Computer Music, which was written by Matthews for MIT Press, 1969, where he kind of decided to sit down and sort of document all the things that he developed and learned about this. But it's a book, and so the first time I saw the code, I was like, well, I wonder what that sounds like. Like, what does that, how does that work? So I decided to do what everyone who's like facing a deadline to prepare a conference talk would do, and I went on a massive yak shaving exercise. So a friend of mine, Tom, is very interested in compilers and compiler theory, and so we got together and we spent a day trying to write a compiler that would take this simple music program and turn it into audio that we can hear using JavaScript and Web Audio API. And so this is what it sounds like when we did that. The code that I wrote to generate that is on GitHub. If you'd like to play with it and kind of see how this language is implemented, I'll give you the link to that at the end. But it turned out that going through the exercise of developing this compiler and turning this language into audio wasn't entirely pointless. I think doing it, I learned more about how web audio works and some of the principles behind web audio and where they come from. And so I'm going to talk a little bit about that for the rest of the talk. The first thing that I learned by doing this was that if you provide flexible building blocks within your programming language, in your music programming language, you enable people to do very creative things. So the basic building blocks of the music language are quite simple. For example, we have oscillators, which you can give a frequency and an amplitude. It's not quite as simple as just giving them a frequency and amplitude. You also have to worry about the frequency they're operating and aliasing and band limiting and so on. So Matthews describes in his code, and we use it in web audio, in the Gecko and WebKit implementations of web audio. They have the same thing. They have like band limited oscillators. So you can say, give me a sound at this frequency, and you don't have to worry about aliasing and things that you don't want in that sound. In addition, Music 5 also let you define random functions, such as just generate random noise, white noise generators, sample and hold signals, and so on. It let you talk about envelopes, which are how you vary a parameter over time. So music allowed you to do this like at the rate of the audio. So you could change the value of a parameter or the amplitude of something like every single sample. It turns out that it's more efficient to do that at a lower rate, and you can do more kind of real-time control, and so web audio lets us do that at kind of control rate as well as audio rate. It defined filters which allow you to modify the sounds by subtracting some of the frequency content. and it's quite complicated to get that right in practice, to have filters that sound good and do what you expect them to do. And the book and the Music 5 language kind of solved that and gave you a kind of building block where you can just say, well, remove everything as far as practical over a certain frequency. The music language allowed you to add and multiply signals together within your instruments and combine them in ways. And one of the things that I found really interesting was that while all of this work was happening at Stanford and Bell Labs with the development of the computer music programming language, there was also a movement in the kind of analog synthesis world to develop, by Bob Moog and people like that, were developing these kind of modular synthesizers, which were ways of like plugging together signal generators and filters and so on in a kind of big modular way. And one of the things that everyone did when the Web Audio API first came available is to kind of go out and try and recreate the sound of an analog synthesizer. It's like the kind of the project that everyone wants to do. But it's really fun to note that like the digital kind of modular equivalent that was developed in music by patching things together and connecting together actually predates the analog. And there's quite a lot of evidence to show that Bob Moog, who was visiting Bell Labs, was kind of inspired by the computer program that was being developed to kind of use that modular synthesis approach in his synthesizers. The second thing I learned is that music allows you to extend things in the right areas. So you can combine these kind of pre-existing, pre-built building blocks in creative ways, but you can also extend them. So we saw before that you could create a generator for a waveform to use in your oscillator. So you could replace the waveform of the oscillator at any point and the shape at any point in time. And the Web Audio API also has this capability of allowing you to specify the wave shapes that you use in oscillators, but also to control parameters over time. So it has this extension. The unit generators and Music 5 as a whole were implemented in FORTRAN to target kind of assembly language for the mainframe computers they were working on. But if you wanted to, you could define your own ways of generating sound using FORTRAN subroutines. At the time that these programs were being developed, it could take 100 seconds of real-time, like clock time, to generate just 1 second of audio. And you probably didn't have access to your own computer, and maybe even in your own lab, let alone on your own desktop. So you had to pay for access to a computer and take the music compositions that you'd written down to kind of a mainframe and feed the punch cards in, and that would cost you like hundreds of dollars an hour. And I was surprised to learn like how much kind of metaprogramming these early computer music languages allowed. So there was a kind of temporal metaprogramming language which let you talk in terms of beats and tempo and timing that was more natural to musicians, and then it would translate that code into seconds and so on. So there's this sort of level of like a pre-compilation step. And you could also write your own subroutines that generated the sound as well. And this, you can see the clear influence in what we have with Web Audio. It's sort of there's a lot of desire from developers to be allowed to kind of develop their own sort of processing code in JavaScript, and that's something that was thought about early on. So Music 5 is very influential on the development of kind of digital synthesis techniques, and so I wanted to give an example of what all of these principles allowed someone who's a kind of skilled musician and programmer to achieve. I'm going to talk about Jean-Claude Risset, who was a musician who worked with Matthews at Bell Labs. And he conducted a series of experiments where he measured brass instruments. And so he realised that when you record instruments and people playing brass instruments, that the harmonic content, so the frequencies in the notes, depends on the pitch of the note, but also kind of how hard you play the note and how long you play it for. So there's a lot of kind of the performance parameters going to generate these notes. And so he kind of did this study of how brass instruments worked, And then he worked out how he could synthesize brass instruments using the oscillators, filters, and envelopes that were provided in the music programming language. And he was able to create quite authentic syntheses of these instruments. So I'll just try and play a little example.
201.
I think that's it. So that piece of music, number 201, comes from Jean-Claude Risset's 1969 publication. He called it the Introductory Catalogue of Computer Synthesized Sounds. And in there he describes how you can use the music programming language to synthesize brass sounds. But he also covers a whole range of other things. So he experimented with what we'd call now FM synthesis, and he developed a technique that we call wave shaping synthesis now. And he did that all using these kind of simple building blocks that the language provided to him. The thing that's very relevant about the music programming language that we see within web audio today is that it introduced a kind of separation of concerns. So it split your thinking as a developer or as a musician into a kind of declarative and imperative part. So you first declare what instruments exist and how they're built and when, at what times they exist, and then you specify what notes that you play on them. And we see today that that paradigm is very valuable, because it means that with web audio, the browser can provide like a very high performing, low level version that we can just declare how we want to use it to build kind of sounds, and then we tell it what to do. And so it allows for very efficient implementations of the primitives in the language. So when we run the browser in the mobile device, it can be written, the underlying system can be written to kind of work well there. But it's interesting that it's also allowed us to kind of think about executing sort of code that developers provide in JavaScript, like inside web workers or audio workers, where you don't really trust the code that's coming in, and because you've got this separation, you can kind of sandbox it and isolate it. And Matthews didn't have to worry about that at the time, because this was all running, you know, there was just a single thread on a single machine. So I've talked about what I learned there and how I see the connections between the music programming language that Matthews developed and the web audio API as it's being implemented in browsers today. And I just wanted to kind of join the dots there and show a few examples of technology in the intervening kind of 50 years that sort of bridge that gap. So the music language that Matthews developed spawned a whole family of variants, and they were written in different languages for different machines. So Music 5 was the first of the variants of his language to have this kind of graph and block orientated structure, where you kind of talk about that separation between declaring your instruments and what you want to play on them. But later on there was a variant of that language called C Sound, which very much takes these principles, and you can kind of define instruments and the notes that you play on them, and that's still used very much today. It's in continuous development, and it's very powerful. And along the way, as the technology and the interfaces improved, the people working on them realised that this unit generator concept of like connecting blocks together to build instruments was ideally suited to graphical interfaces that were being developed. So here's a screenshot from a program developed at MIT called MIT Syn, where you could actually kind of drag and drop and connect these kind of blocks together. And that was developed further into the Max language. If people play with Max MSP, that's very much a similar paradigm. And Super Collider, which is very popular, is kind of a Lisp-like dialect for doing this too. And that was developed by James McCartney. Chris Rogers, who was the person who originally specified the web audio API at Google, he'd worked with James McCartney at Apple. James McCartney's developed a Super Collider, and so he was very much influenced by that kind of work. and they were working on the core audio system of what became OS 10, and building a lot of these principles. So if you've kind of worked in core audio a little bit, it also has this kind of paradigm of connecting together processing blocks. So when I gave this talk, I think I was talking to an audience of people who, a lot of people, they criticize the web audio APIs it's been developed as kind of not giving them the power that they want, and not giving, they say, why can't you just give me samples and let me operate on them? And so I kind of wanted to illustrate that many of the decisions that went into the web audio API are kind of based on this sort of long history of working like this, and that there's a lot of things that you can do with these paradigms that allow you to kind of be very, very creative. But it's also designed to be kind of extensible and to be allowed to extend it with your own code and your own parameters and by connecting things together. And so music kind of got this balance right, I think, and what we have now is sort of a continuation of that. But Risse, who we spoke about earlier, was very aware that just because you had more powerful computers and more powerful computer music programming languages, that didn't mean that you were going to make better music. And so he said that music is not an arms race. Max Matthews died in 2011, but shortly before he did, he was interviewed about the kind of future of computer music. And he said that almost any computer that anyone has today has thousands of times more power than anyone knows how to use in a musically useful way. He said musically useful means making things that really light up people's pleasure centres, that they think are beautiful or expressive. The limitations and the domain of future progress lies in better understanding how our brains work for music, to work out why we love music and what we love about it. And I think the thing that really excites me about web audio and putting this kind of technology in the browser is that it kind of gives anyone who has a browser this access to a universal instrument, and they can kind of help us to answer that question. On my website I have a blog post where I kind of link to some of the papers and demos and things that I mentioned through here, and you can go and have a look at that compiler that we wrote, and see if you can write your own pieces of music in the music programming language.